confusion about the sign last time. Actually, I looked at the notes. There is only one term which you need to fix the sign. Everything else in the notes are consistent. I don't know if you have already spotted that, but this is, in any case, it's an equation. There's a typo in the equation 4.38. All you need to do is to change the signs of A and B. Then the rest of the thing is constant. Okay?
Sorry, could you repeat?
4.38. Equation 4.3a. The signs of A and B should be opposite to what it has been typed. This is the problem with copying and pasting sometimes.
I think there are other typos. I explained it.
Yeah,
I can hear in these equations. Okay, it's minor bands. We should put this. This is the.
Yeah, you're right. You're right. Yes, thank you.
Okay.
Can you send them by an email to me? You have another people?
Yeah, actually, in the vertex correction section, there should be integrals.
Yeah, that I have corrected. Thank you. I have noticed that on the correction. You're right. But that the notes that I am giving you, by the way, last time I gave you notes which also had the vertex correction, no? The typos like that have been corrected in the new version. I am giving you the same vertex correction again, but a lot of typos have been corrected. So just forget that and use this one in order not to be confused. Okay? So the notes that you will receive today, hopefully will have less of that kind of typos. Okay, today's topic is to just sum up what we have been doing on the renormalization of the scalar field theory, and what we are going to discuss, among other things, is coupling constant renormalization. Or vertex correction. And for that, I will change the model. I will discuss phi to the 4 for a very simple reason that it needs less calculation. We have done almost all the calculations needed to discuss it. We have already done it. So we don't need to do any extra integrals, etc., etc. So we can just discuss the conceptual side of it. But also this gives us an opportunity to sum up what are we doing by writing the bare field, etc., in terms of the renormalized field. So this is the last time I'm going to write this section, but let me write it for the last time. We start an action. Let me write in 4 dimensions, which in terms of the bare field, which I'm denoting with this symbol, it looks like this. And today we will discuss phi to the 4. Okay? We put a lambda 0 here. Then phi is replaced in terms of a renormalization constant z times renormalized phi. Usually people put also an r here, but we are going to drop it because I'm denoting the 2 phi's differently. And this is written as, okay, so in the first step you do this. You substitute here, and you see that there is a z from here, square root of z from here, and square root of z from there, and therefore a z will enter here, which we are going to write as 1 plus a, or we did write as 1 plus a. Okay? And here there will be a z squared. So the idea is use this one part to separate this action into a part and which is written in terms of the renormalized field, renormalized mass, renormalized coupling, plus the rest, whatever is the rest. And then apply perturbation theory. the upshot of all these substitutions, rewriting, eventually is the following. So when you write the same action in terms of the renormalized objects and separate the one piece from here like that, and write the mass also in terms of the renormalized mass, the coupling in terms of the renormalized coupling, then all the rest which comes from substituting the bare objects in terms of the renormalized objects boil down rewriting the same terms except that with coefficients which are different from here. There's just some constants. So we will have a term like, you can parameterize these things in various ways, okay? But the way I'm parameterizing it is like that. The effect of all the rewritings is just to add to the action precisely the terms that you have, but with coefficients A, B, C, A, in this case 3 coefficients, A, B, and C. You have 3 objects, phi 0, m0, lambda, and you have 3 constants, A, B, C. Now you can rewrite the way you like. Different people write them in different ways, but eventually you can redefine the parameters and bring it to this form. Some people, for example, separate this t squared from m squared and combine this m squared with this thing. But that will replace simply p by p prime, some other number. Okay, it doesn't matter. I find it more convenient to write in this way. Okay? Now, as I mentioned last time, these A, B, C are not new parameters. They are determined by imposing renormalization conditions in terms of m squared and lambda and cutoff. And sometimes renormalization point, which I think the mu squared, that in dimensional regularization introduced. But they are not independent objects and they are not going to be measured. The only thing which should be measured is lambda and the scattering cross sections and the mass, the physical mass. Okay? So far we have been, the m squared that we have been using, we have introduced, is defined by the pole of the 2-point function with a very specific residue. So that guided by spectral representation of the 2-point function, we called it the physical mass. Later on we will see that you can introduce other mass parameters, renormalized mass parameters, which are not necessarily the physical mass. They are pole mass, for example, they're called. But that's okay. For time being, let's just stick with this. Is this clear so far? So the bottom line is this. Let's write the original action plus extra terms, precisely with the same functional form, but with coefficients A, B, C, and the determined coefficients A, B, C by imposing renormalization conditions. And this process should be done order by order in perturbation theory. You cannot determine them in one go. You will do it at one loop order, then when you go to the 2 loop order, these parameters, I wrote them as power series in lambda, the coupling constant, then the coefficients of those power series will be fixed order by order in perturbation theory.
In this action, you actually meant to wrote that phi.
The other one.
I'm sorry. Yes, I'm sorry. You should have told me when I was writing. Thank you.
I noticed just now.
Thank you. Yes. I meant renormalized phi. Sorry. That's correct. Okay. Did I make other errors? Is that all? Okay. That seems to be more so far. Okay? Now, let's move on. What we want to do is, in the previous lecture, we determined A and B for phi cube model. Today we are going to determine C. And the reason why I wrote 5 to the 4 is the phi cube is slightly shorter the calculation. If I did that, I had to write plenty of things on the blackboard, okay? And it would take most of our time just writing integrals. But before doing this, let me go back to another issue which I mentioned several times, and I always postpone to explain it, and probably today is the right point to explain it. And this is how we separate renormalizable theories, how we distinguish renormalizable theories from non-renormalizable theories. What is it which distinguishes them from each other? You see that the whole problem arises from ultraviolet divergences. You have loop graphs where you have to integrate over the loop momentum. Loop momentum goes from minus infinity to plus infinity for each component of K, the loop integration value. And usually it is the infinite limit of the loop momentum which takes the contribution of the short distance modes or the high energy modes into account, and that they make the diagrams to diverge. That's the origin of all this machinery that we have invented, or people have invented 50 years ago. And therefore, in order to find out which class of models can be rendered finite by imposing a finite number of renormalization conditions at all orders, and which class cannot be done in that way, we have to go back and look at the general structure of the loop graphs. So a useful tool for that is something called an index which is associated to each graph. So associate to each graph an index or a degree, an index D, which is defined in the following way. Every graph has a number of loops in it. So let's denote by L the number of loops in a graph. We are considering one specific graph. Okay. And it also has a number of propagators in it, and that number we are going to denote by I. So the loop graph will contain L powers of D4K in the numerator and 2I power of K in the denominator. This is not, of course, precise calculation. I'm just counting the powers of, roughly, the powers of the, not roughly, exactly, powers of the loop integration variables and the powers of K, which stands in the denominator because they come from the propagators. Each propagator has a K squared in it. And if there are I propagators, it will be K squared to the power I. And the index, the definition of this index is 4L minus 2I. The most obvious thing that you can associate with the graph. Obviously, if this D is positive, the number of the integration variables in the numerator is bigger than, non-negative, not positive. It can also be 0. The number of the integration variables in the numerator is more than the powers of K in the denominator, or equals to the powers of K in the denominator. And for a large value of K, that integral will diverge. Okay? If this is negative, the integral can be convergent, but it doesn't need to be convergent. And we will see why. You will see the example where a graph has a negative D, but the integral still is divergent. Now, for this reason, this is called superficial degree of divergence. The reason for the word superficial is that it can be negative and the graph still can be divergent. That's the reason why it's called superficial degree of divergence. We'll come back to the superficial aspect of it in some minutes. Now, what we are going to do is to write this in slightly different form. Here, the way I've written it, it depends on the number of loops of the graph and the number of the internal lines, etc. It is more convenient, as you will see, to write it instead in terms of the number of the external lines of each graph. Every graph has some number of external lines and the number of vertices. Okay? So the definition is this. We are only going to rewrite it in terms of number of the, this is number of external lines and V is the number of vertices. I am not considering derivative couplings, but you can also consider derivative couplings. And I am fixing 4 dimensions, but you can do it in arbitrary dimensions. That means in a general theory, you can have fermions, vector bosons, scalars in arbitrary number of dimensions, and arbitrary number of derivatives acting on them. This is the most general thing that you can construct with fields of spin not greater than 1. Okay? And it's a good exercise actually to write down these more general couplings and examine the problem, see what happens. But let's, for time being, let's assume that we have an interaction Lagrangian with phi to the power L. And I'll take L to be an integer, a positive integer actually. Okay, so we start from a model with such kind of interaction Lagrangian in 4 dimensions, and these are the parameters which characterize every graph. The definitions are clear? Now, these, of course, these numbers are not all independent from each other, because they pertain to the same graph, and you see that, for example, since the power of phi is L, from each vertex, how many lines go out? From each vertex, there are L lines which go out of each vertex. So the total number of lines going from all the vertices of the graph, since there are L vertices, is L times V. Well, these lines are going to end. Either some of them will be external lines and some of them will be internal lines. Each line is either an internal line or an external line. Therefore, this total number should be the number of the external lines plus 2 times the number of the internal lines. For propagator, you show 2 vertices. Therefore, it's 2 times internal lines. So this tells you that I can be expressed in terms of these 2 parameters, because remember that we want to express D in terms of number of vertices and number of external lines. So we eliminate I from there, and the simple algebraic equation gives you I in terms of number of vertices and the power of interaction and the number of external lines. Likewise, L can be expressed in this form, the number of loops, because the number of loops, let me put it here, the number of loops for loop integrations is the number of the internal lines. For each internal line, you have a loop integration. But then there are V vertices, and with each vertex, there is a delta 4 associated with the vertex, which you can use to perform some of the integrations. Eventually, one delta 4 will survive to ensure the overall conservation of energy and momentum 4 vector. So the number of loop integrations, therefore, is I minus V plus 1. This one is a surviving delta function, which is eventually will, which ensures the conservation of the loop momentum. So you can substitute for I from here and express L in terms of, okay, this simple algebra is in the notes, I'm not going to write it. Writing I and L in terms of V and E, plot this back in star. So substitute I and L from equation 1 and 2 in star. This is 1 and this is 2. And do the simple algebra, the result will be 4 minus E plus L minus 4 times V. Okay? You don't want me to carry out these steps, no? So this is our result. And it's from here that we are going to extract which models can be renormalizable and which cannot be renormalizable. The first thing we note is that L minus 4 is in fact the dimension of the coupling which will stand here. The dimension of this lambda L. In fact, the mass dimension of lambda L is 4 minus L, as you can easily work out. If L is 4, this will be dimensionless. So therefore, we write this relation using that there is a minus sign difference between the two. This becomes the dimension of lambda L. So D becomes 4 minus E minus dimension of lambda L times V. This is the basic relation. Now, let's look at it first of all, let's work out an example. The example is just replace L by 4. This is this model, and see what's the outcome. So if L is 4, lambda L, the dimension of lambda is 0, and we get a very simple relation. The simple relation is that, this is example. L equals to 4, lambda L equals to 0. That's this model here. And therefore P equals to 4 minus E. What does it mean? It means that the number of the graphs which have positive T or non-negative T is actually very small. It's for E equals to 0, 1, 2, 3, 4. As soon as E goes above 4, the degree of the divergence becomes negative. Okay, the graphs which have the chance to be very divergent are for E equals to 0, 1, 2, 3, 4. And let's examine each case separately. E equal to 0, that means a graph with 0 external lines. This is just a constant. This is the constant. In fact, it's the sum of the 0-point energies of the Hamiltonian. It's a so-called cosmological constant, if you like. You can renormalize it by adding to the Lagrangian a constant term and removing that infinity. It's an infinite quantity. You know that the sum of the 0-point energies is infinite. Okay? We are not doing it because we are not concerned with gravity. If there is a gravity in the problem, this is a major problem because it's a big constant. It will contribute to the cosmological constant. It's a so-called cosmological constant problem, one of the unsolved problems of physics. So that is that contribution. The next value of E is 1. But the graph with one external line in this model is what? 0. Why is it 0? Because of the Z2 symmetry. There is a Z2 symmetry. So you will not have any graph with one external line in this model. This wouldn't be the case as we saw last time in phi cube. No? So that doesn't give us a problem. The graph with e equals to 2 has two external lines, and we saw at the one loop level, this is the graph for this. Well, in phi, that's the graph in phi cube. Here, this is leading over the contribution. These are divergent graphs. It has e equals to 2, and therefore d equals to 2. If you introduce a cutoff, the number of the momentum integration in the numerator minus the ones in the denominator is 2. That means that it should go like cutoff squared. So for that reason, these are called quadratically divergent. And we know that there is a renormalization counter terms for them, A and B. We should fix them. When we say that an expression is quadratically divergent, it doesn't mean that all the divergences will be quadratic. For example, here, if you look at various terms, you can see what the divergence of each graph should be. I leave it to you, these two, to work out, to think about it. Let's look at this one. You see that there is 1, 2, 3. Okay, there are 3 propagators here, and there are 2 loops. If you think about it, you will see that actually that will contain, I mean, if you examine it, it will contain the quadratic and the logarithmic divergence. Not just quadratic, but quadratic and the logarithmic divergence. The logarithmic divergence will go to contribute to A, and the quadratic divergence will contribute to B. Just think about this. The reason why we did phi cubed in order to calculate A, the wave function renormalization, was that if we wanted to do phi to the 4, the first non-trivial contribution to A would come from this graph. And this graph is more complicated than the graph we calculated. Yeah, I wanted to push one calculation to the end, to calculate A right to the end. If we want to do phi to 4, we have to come to this graph in order to calculate A. These will not contribute to A, they will contribute to B. And these are trivial to calculate. So as a simple exercise, so this is a small exercise for you. Calculate the contribution of 1 and 2, this is 1 and this is 2, to B. Why do they not contribute to A? Why do they will not contribute to this renormalization constant A? Okay, think about this. So that's another part of this exercise. Do they contribute to A? Find out the answer for that. So the next value of E is 3. E equals to 3, what happens here?
0.
Again, it's 0 because it is the odd number of external lines. Finally, when we reach E equals to 4, E becomes 0, and it can only contribute it can only be logarithmic. And so then you have 4 external lines, the simplest graph with 4 external lines is this, which obviously has no divergence, but the next one could be like this. This is the graph we are going to study today. Okay? And we will see that indeed it's divergent. We will not introduce a cutoff, but we will use dimension regularization, but nevertheless, this graph has to be, in fact, will be divergent. So, to remove the divergence or obtain a finite number from this graph, you will need to impose the renormalization condition on the 4-point function, and that will determine for us this constant C. Okay? Which we are going to do. Now, the final point before we go and calculate C up to the one loop level, the final point is to come back to the meaning of superficial. That means, let's consider a graph which is superficially convergent. It has negative d. If it has negative d, it means that the power of the momenta in the denominator is more than the number of d4k's in the numerator. So you expect that graph to be finite. And let's just take the example of E equals to 6. The graph with 6 external lines. This graph with 6 external lines will have d equals to -2. So you expect it to be finite. But let's see if it can be finite. You will see that, in fact, it is not finite. Nevertheless, you will not need more counter terms than what we have written to make it finite. And that's the hallmark of Renormalisation. So, let's consider this graph, which has 6 external lines. One, two, three, four, five, 6. It has 6 external lines. Now, this graph, we know that it cannot be finite as it stands. Why? Because it has subgraph like this, which by itself is divergent. So, if you just put your attention on this, remember that we are calculating functions for which the external lines are not on shell. That's one of the uses of the off-shell Green's function. The endpoint functions that we are constructing, the external momenta are not on shell. If you are calculating S-matrix elements, we have to put external lines on shell, but not for the endpoint functions. So this object is like this graph. Here, the external momenta can be anything. They are not restricted by anything. So if you cut it from here, you see that this will be divergent. So by itself, this part is divergent. Therefore, it will make the whole thing divergent, because the result is the product of what you get from here and what you get from the rest of the graph. If one component is divergent, the rest will be, the whole expression will be divergent. Right? And yet, it has d equals to -2. The reason this is the origin of the word superficial, I guess. Why it's called superficial degree of divergence. The point is that if you stop here, you will get divergent. In fact, you will get an infinity. But you shouldn't stop here. Our rule is that with every graph, you also must add to the graph all possible counter terms. Now here there is a counter term. That counter term, we are putting sort of field dot here for the counter term, will be obtained from this graph replacing the vertex by a counter term. And if you do that, you will obtain, I mean, not the vertex, but the whole, this part will be replaced by the counter, and you obtain something like this. So if you take the sum of two, and this one we will fix today, that means this is the value of C at the one loop level that we are going to determine. This is what I was trying to explain last time. If you fix the C at the one loop level, this is a two loop graph, right? And put that value that you have already determined at the one loop level here and take the sum of the two. Means take this graph plus minus IC times lambda, this vertex is minus IC times lambda, plus the rest of the graph, and take the sum will be finite. If it wasn't finite, if you couldn't get a finite number from here, then obviously in order to make this finite, you would need a term in here with 5 to the 6. This has 6 external lines. For this you need a counter term with 4 phi's in it, which is this. For the 2-point function, you need a counter term with 2 phi's, 1, 2, 1, 2, to fix A and B. In order to fix the infinity of a graph like this, you would need a term in the action with 6 powers of phi, which we do not have in this action. We do not have it because we don't need to have it. Without having that term, if you do this properly and take account of all the terms that we must keep in mind, we must include in the calculation, then you will get a finite term. You don't need an extra counter term for that. So the bottom line is that in this class of models, you have a finite number of so-called primitive graphs. The primitive graphs in here are the 2-point function. If you discard the cosmology constant, or the e equal to 0 case, they are the 2-point function and 4-point function. What we need to determine are the renormalization constants A, B, and C at each order of perturbation theory. After you have done that, use them at the next order. And be careful to include all the graphs when you go to higher orders, including the counter terms. And then the sum will be finite. To see the difference, what happens with the non-renormalizable theory, let's go to the formula again. So do you have a question at this point? No? So let's go back to the formula for superficial degree of divergence and write it again. So the formula was D equals to 4 minus E minus mass dimension of the coupling times the number of vertices. The case we considered was lambda L equals to 0. For phi cubed, lambda L will be equal to 1. Okay? And you see that for phi cubed, the superficial degree of divergence has more tendency to be negative than positive, because not only E subtracts from 4, but also V, as you increase the number of vertices, D quickly becomes negative in 4 dimensions. If you examine the same thing in 6 dimensions, it will be more or less similar to what we did for phi to 4 in 4 dimensions. Therefore, phi cubed in 4 dimensions, in a sense, is a trivial theory, because essentially all the graphs, apart from 2-point function, has superficial degree of divergence, which is negative. Okay? In 5 to 4, you have 2 classes of primitive graphs: the 2-point function, 4-point function. Here you have even less. But the interesting case is if there is a model for which lambda L is actually negative. So the examples which I gave you, one of them is 0, the other one is positive. 5 to the 4 is 0, phi cubed has a positive lambda L. But consider another case when lambda L is negative rather than positive. For example, if this phi to the L, if L is more than 4 in 4 dimensions, then lambda L will be, lambda L was 4 minus L. If L is more than 4, lambda L would be negative. Phi to the 6 in 4 dimensions, for example. Okay? In that case, this term, lambda L being negative, this term will be positive. So in this case, D equals to 4 minus E plus, how should I put it? Absolute value of lambda L times V. right? In 4 dimensions, if you increase E, that term is absent, very quickly you will reach a situation where D becomes negative. In 4 dimensions, if this is the model, no matter how large E is, because E has the tendency to make D negative, right? How large D is, you can just increase the number of vertices and make D positive. That means the number of primitive graphs which have positive D actually can be made arbitrarily large simply by adding more vertices to the graph. This doesn't happen in 5 to the 4 in 4 dimensions, because this term completely disappears from the consideration, disappears from the equation. So the degree of divergence of the graph depends on the number of external lines, which comes with a negative sign, and as soon as you go above 4 external lines, this object becomes negative. Here, there is no way that, no matter, take as large an E as you like to make this negative, but then add more vertices to make it positive. So, this is the class of theories which are called non-renormalizable. This is the reason I mentioned a couple of times in the previous lectures that in order for a model to be renormalizable, the mass dimension of all the couplings in the Lagrangian should be non-negative, either 0 or positive. M squared can be considered as a coupling, and it has mass dimension 2, plus 2. For 5 and 4, lambda has the mass dimension 0. In QD, in natural units, the gauge coupling has mass dimension, what's the mass dimension of the electric charge in H bar equal to 1 equal to C equal to 1 unit? 0. So there is one coupling constant which has mass dimension 0, and then there are the mass terms. This is not sufficient to say that QED is actually renormalizable. You have to, because when you apply a similar formula QED, you will find out that a graph like this is superficially divergent. You can define D for QED. Okay? The superficial degree of divergence can be defined also QED. If you make the power counting, you will see that this must be logarithmically divergent. There are 4 fermionic propagators, so they contribute k to power 4 to the denominator, and it's one loop graph. There will be a D4k. Therefore, you expect to get a logarithmic divergence term from here. And to remove this logarithm, if it were there, to remove it, you would need a term with 4 powers of a in the QED Lagrangian. We do not have in QED Lagrangian a term with 4 powers of k, 4 powers of a. There is f squared. How many powers of a it has? F mu squared. 2. F mu has 1 power of a, and F mu squared has 2. And then there's the gauge coupling times the interaction term. There is no term purely with 4 powers of a in QED Lagrangian to be renormalized to remove a divergence like this. And if this graph was divergent, QED would be non-renormalizable. The action that we write would be non-renormalizable. But what happens is that these are vector bosons. So to be gauge invariant, they should come in a specific combination. We know that the combination in which they should come is F mu nu. That means this graph should go like F mu nu to the power 4. There are 4 A lines, and if each F has one A line in it, therefore it would go like F mu nu to the power 4. What's the dimension of this object? F nu to the power 4. F nu squared has dimension 4. Therefore, this would have dimension 8. So to go into the action, the coefficient in front of it should be minus 4. Okay? So the gauge invariance rescues it. In fact, we will calculate this then. Not in detail using Feynman graphs, which is an impossible task, but by other means. And you will see what's the coefficient in front of it. You will get a finite number for the coefficient. As I said, not by calculating Feynman graphs. I mean, that's quite difficult to calculate using Feynman graphs. Okay? So,
from the QED course, we are familiar with water entity. So if we just replace water entity,
that's true. That's true. That's another way of saying it. I wanted, in this context, I wanted to use the power counting argument. But what I just said is a result of word identities. Did you discuss word identity in QED?
Yeah.
Ah, good. So I don't need to discuss it. That's good to know. That's very powerful. The word identity puts a lot of constraints on the things that can happen. Okay, now let's go and actually calculate this after. Any questions on this? Good. So the calculation will be quite fast because, first of all, we are looking at 4-point function. Let's draw the graphs. The graphs which will contribute at the tree level, it will be this. Then there will be one loop graphs. Now, it will be this one, but then there will be two more graphs. Where do they come from? Of course, they come from Feynman rules, the application of Feynman rules. But they also come from the fact that the 4-point function has to be symmetric under the exchange of various coordinates. And that's the origin of it, that if you write in the position space, there should be 3 terms added to each other, which should make everything symmetric at the end. We can calculate the 4-point function here. That's what we did for the 2-point function. Means the external lines in that case are propagators. Okay, in all of them. But you can also calculate S matrix elements. This is in fact a sort of very good point to show how we go from one to the other. If you wanted to calculate the scattering amplitude of 2 particles, scattering amplitude of 2 to 2. 2 particles coming and 2 particles going out. The graphs should be identical if you don't say what the external lines are. If you're calculating a 4-point Green's function, there should be Feynman propagators on the external line. If you're calculating an S matrix element instead, the external lines should be the wave functions of incoming and outgoing particles. And their momenta should be unshelled. Okay, that's the only difference. This is the reason why, if you have information about the endpoint functions, you can go from endpoint functions to the S matrix element. There is a formal way of doing it. There's a mathematical formula which takes you directly from endpoint function to S matrix elements. But graphically, it is obvious. All you need to do, the type of graphs is absolutely the same. The combinatorics is absolutely the same. The only thing you need to do is to say, what are you going to attach to the external lines? If you're going to attach the unshelled momenta of the incoming and outgoing particles, you are calculating the scattering amplitude. If you attach to them Feynman propagators, you are calculating 4-point functions. In either case, the non-trivial part of this calculation is not the external lines, because we know what they are. The non-trivial part is this piece here, the loop part. This, of course, has not much to calculate. It's just the vertex times whatever is attached to the external lines. But this one has a loop integral, so we have to calculate it. The difference between this graph, and this graph, when you write them in the momentum space, is just the attachment of the momenta to various graphs. So this one I will label as like this one, P1, P2, P3, P4. This one will be P1, P2, P3, P4. These ones are obtained from here by cyclic permutations of 1, 2, 3, 4, 2, for instance. You put these external momenta in permute them. And then you obtain. Our final rules tells us that we should also include the counter term. So there will be a counter term vertex. This is the minus I C lambda term associated with that. Okay, so first of all, if you are calculating scattering amplitude, the external lines are unshelved. So Pi squared will be equal to M squared, and M is the physical mass. And as a consequence, this graph, for example, the whole amplitude will depend on the square. First of all, it should be Lorentz invariant. So there is a total momentum which is going in P, and the whole amplitude, if you denote it by, you are going to denote this by minus comma 4. There will be minus comma 4, which will depend on P squared or S. You remember the Mendelssohn variables. S is P squared. There is a T, there is a U. T with this graph and U with this graph. I will leave them to you to write them in detail. And you remember that they are not independent from each other. There was an exercise I gave you in September to show that their sum is equal to 4m squared. Okay? So by Lorentz invariance, these graphs should depend on TUS. The first one is the one that depends on S. So that means the entire amplitude, which I'm going to call minus IM, will depend on STU with this constraint and STU. And if the notation is confusing you, please stop me. Don't let me go. And if I'm also writing something which doesn't look like correct to you, please submit again. So let me erase this part of the blackboard. So apply Feynman rules to the first graph. You don't need to do it separately for other graphs because they are obtained from each other simply by changing S to T and T to U. So the first graph, this one, there is S, the total center of mass energy. We define comma 4 by the relation here. Note that I'm not going to put the lambda in the definition of comma 4. Lambda will come. This graph will go like lambda from here and lambda from here. So it will go like lambda to 4. I will bring in later on. Let me just write the parts which is essential to this discussion. First of all, in dimensional regularization, we introduce normally this mu, the mass parameter, to keep the parameter interaction, the coupling constant, dimensionless. And the power on this is to absorb the dimension of the bare coupling in n dimensions. We are going to apply dimensional regularization. Let me put it here, not to forget it. So apply dimensional regularization. This means that we are going to define a delta which is equal to 4 minus n. I called it delta because I had called it eta in 6th dimension. In order not to confuse with 6th dimension, I'm introducing a new symbol called delta. And lambda 0 is mu to power delta divided by 2 times lambda. The graph goes like lambda squared, therefore there is a power of mu to the power delta. There is 1/2 which comes from application of the Feynman rules. This is the combinatoric factor associated with the loop. Then there is a loop integral in n dimensions. The rest is put the propagators for the two lines, p plus k. This is p plus k, this line, and this is k in this line. And p is the total momentum which goes in. Okay? This is the definition of gamma S, if you like. This is precisely the integral which we encountered when we were studying the two-point function of phi cube theory. The only difference is that there we were interested in the value of this integral when n was approaching 6. Here we are interested in the value of this integral when it's approaching 4. But the rest is identical. And since we calculate in n dimensions and obtain it in terms of the gamma functions, the gamma function, not to be confused with this, let me put the label 4 here, not to confuse this with the gamma function. Therefore, the formula can immediately be taken over from what we have done before. Okay? So we don't need to calculate this integral again. Apply the Feynman trick, put the denominators together, convert into a single denominator for the power 2 on the bracket, and copy the formula from what we had before. I seem to have lost some page. Okay. So first of all, let me write here what is it that we are calculating, and then go back there. So we are calculating the sum of these three graphs. In fact, we are calculating the sum of this term, this term, this term, this term, and this term. We are calculating the sum of all of them, and the amplitude we denoted by IM or minus IM. You will find it in the notes. The coupling constant factor I am putting in front, not including in gamma. And here, the contribution of this graph is I comma S. The contribution of this other graph is I comma 4t. And the contribution of this graph is I comma 4u, plus the contribution of constant minus I c lambda. Obviously, all these graphs will be expressed with the same function, but evaluated at different values of its argument. This argument is, here it's the total center of mass energy, and here they have the interpretation that you must be familiar. No? Bands and variables. So this is the expression, the one loop expression, or the expression up to one loop for the two particle scattering into two particles. The three level, one loop expressions, and constant. What we are calculating here is just this function gamma 4s. If we know it, if we know the form of this function, then of course we know all three of them. Okay? Fine. So I will copy the result of the integral in a minute, but before doing that, let's just make a pause and ask what is it that's going to fix C for us. In the case of two-point function, we were guided by spectral representation of the two-point function and the fact that it has a simple pole at the physical mass with a very well-defined specific residue. Here, we don't have anything like that. There is no spectral representation for the four-point function. In fact, we have to impose a physical condition in the sense that this coupling, you see that at the tree level, it is precisely the scattering amplitude of two particles to two particles. It's the trivial part of this calculation. The condition we are going to impose is that for some value of S, T, and U, always subject to this constraint that I erased because the moments are on mass shell, the value of n is going to be equal to this lambda. That means lambda, so the renormalization condition you can invent other renormalization conditions, and hopefully if there is time today I will mention them. But for time being, in order to proceed, we will say that the condition we are going to impose is that m evaluated at a value S0, T0, and U0, just pick up some specified values of these parameters and declare the value of m scattering amplitude to be lambda, or lambda to be given by that. This is the way that the experimental is going to measure. These P1, P2, P3 are controllable parameters. These are the energy and the momentum of the incoming particles. When you are making an experiment, you know what they are. So at some given value of S0, T0, U0, the scattering amplitude which is going to be measured is going to be declared to be equal to lambda. This is just a condition we impose. We can impose other conditions as we shall see, but this is one possibility. If you do this, then put that condition there. So this means that on the right hand side there is an I here which I can drop, and that gives you -1 or minus lambda squared. In fact, what you need to find out is IC lambda. So impose this condition, and here this lambda will cancel that lambda, and you'll find out that IC lambda should be equal to, let me write the whole block because we are going to need it. I, 4 is 0 plus I, 4 T0 plus I, 4 U0. This expression is imposing this condition and this relation. Is it clear? The numbers, if you set these values for STU, this term cancels there, and then the sum of these two terms must be 0, and that gives you this. Now take this IC lambda and put back in the original relation. Okay? The first thing you note is that we know that this expression will be divergent, because we know that it will go like the gamma function 2 minus n over 2. I'm sorry that I'm using gamma for both for this and for that, but I think it's obvious, it's clear that. So it's going, each term will have a gamma of 2 minus n over 2. So as n goes to 4, this will be gamma of 0, and we know that this has a simple pole at the origin. So C will depend on the cutoff. Here cutoff is delta. Okay? Second thing is that the claim is that if you substitute for IC lambda here, then the resulting amplitude will be finite. So if you make the substitution, this is IC lambda, here you have a minus sign, so this whole expression will come with a minus sign, and it will give you, I don't know why I keep this writing this I, minus lambda squared, comma 4, s minus comma 4 is 0. As from each comma 4, you will subtract its value at S0, T0, and U0. A simple algebra. If this is not clear, I can explain it more, but I think it should be clear. If you substitute for IC lambda, this expression, this is precisely the same expression as this, in which you have put S by S0, and there is a minus sign there. Therefore, the contribution of this term will be comma 4 S minus comma 4 S0, etc. So, in the expression that we had, the effect of the counter term is to subtract from each amplitude the value of that amplitude at some value of the external momentum. If you remember, the same procedure actually eliminated the infinities from the 2-point function. We replaced pi by pi minus something. Though the something was the first two terms in the Taylor expansion of pi around p squared equals to m squared. Okay? So, in all the cases, you see that the removal of the divergence ends up with subtracting from an amplitude the value of the same amplitude at some point. Why does this subtract the infinity? The answer is very simple. This will go like gamma function 2 minus n over 2. Its value, the same function evaluated as 0, this doesn't depend on s. Will also go like gamma of 2 minus n over 2. More space. The statement that I'm going to make, of course, we are going to explicitly calculate and show that this is what's going to happen. I'm just giving you the result. Why is this finite? It's finite because gamma for S, as we shall see in a minute, will go like the divergent part will be this, independent of S. And therefore, even evaluate at any value of S, it will have the same divergent part. So if you take the difference, the divergent part will disappear. So this is bound to be finite by construction. Okay? So now let's try the explicit expression for gamma, just to see that that's indeed what happens. I mean, I have to be careful here. I have to write delta over 2, but we are going to, this was very rough. But now we are going to do it in more precise terms. So go back to the notes and put the value of that integral that we have calculated when we were discussing the 2-point function. You will discover that gamma for S equals to minus mu to the power delta over 2 1 over 4 pi n over 2 gamma of, as promised, 2 minus n over 2 times an integral from 0 to 1, the Feynman parameter x, a to the power n4 minus n, where we had defined a squared to be p squared minus m squared minus p squared x times 1 minus x. This p squared is s. That's the definition of a squared. So it depends on the total center of mass energy of the incoming particles or outgoing particles. Apply the machine that we did for the 2-point function, namely expand, so gamma of 2 minus n over 2. If you use this definition of delta, is gamma of delta over 2, identify the singular piece in it. We saw that that's 2 over delta minus the so-called Euler constant plus terms with positive power of delta. And put this mu to the power of delta together with this is a to the power of delta. Oops, I messed up the definition, the signs I did. This is a minus 4, sorry. This is n minus 4. So this is a to the power minus delta. This mu to the power of delta over 2 together with this will give you, put them together and expand. The details are in the notes, so I'm not going to write the details. After expansion, let me also multiply this by lambda now. Eventually we are going to calculate lambda squared times gamma 4. So now I multiply it by lambda so that the expression is ready for use. This is lambda squared divided by 32 pi squared 2 over delta minus gamma plus 0 to 1 dx logarithm of 4 pi b squared divided by a to the power 2. So when delta goes to 0, there is a singular piece here plus finite remainder. And clearly, what you want to insert here is lambda squared gamma 4s minus gamma 4 evaluated as 0. The singular piece does not depend on the energy, the central mass energy, therefore it doesn't matter whether you evaluate it as or as 0, it will just cancel out. So the only thing we should, in fact this constant piece also will cancel out, the only thing we should be left is this term. And you see that then also all this quantity here will disappear, and what is left is the overall constant, Copley constant, divided by 32 pi squared. Oops, another integral over dx, of course, is missing from one of the equations here, but the rest is so you get, instead of mu squared, you get the ratio of this function evaluated at s and the 0. See, I have put this overall factor in common. This comes with positive sign, this comes with negative sign. For that reason, that's what you eventually get, if not upside down. I hope these signs are correct. Okay, So let's put the final result together. This is the sign correct that comes with myself. It's outside. I think it should be upside down. It's possible that
This is
Upside down, yeah.
so let me put that plus. Then it's okay. That's another T4. So put it here, finally, to see that amplitude in all its glory. In fact, I don't want to do that because you see that each factor will give you something like this, with S replaced by T and by U. Okay? Let me not do that and spend the rest of the time on the final topic of today. How much time do we have? We still have some 10 minutes, according to my clock. Maybe I should keep this. And eliminate this part. Okay, the issue of, I think the next topic is the issue of the subtraction. So, let's go back to this relation again. We just imposed a renormalization condition in order to eliminate the singular piece from gamma. The singular piece, namely the 2 over delta, 1 over delta part. Which in this case, it also cancels this gamma, etc. But eventually, if the aim is to subtract only or eliminate the singular piece, we can do millions of other things. I followed, for the 2-point function, I followed the path which is dictated by the spectral representation of the 2-point function. But we don't have to do it. If we know how the mass is physically, how the mass is defined, how the physical mass is defined, no matter how you make the subtraction, eventually you can define the physical mass simply by doctoring the expression that you have and bringing it to the fore that from which you can extract the physical mass. But what I want to say is that if you put different renormalization conditions, or if you adopt different renormalization prescription, the expressions which you will get at the end, of course, will not be the same. But the finite pieces will be related to each other by finite renormalizations. You can go from one prescription to the other after you have removed the divergent pieces simply by finite renormalization of various parameters. And on different problems, it may be convenient to impose different kinds of prescription. For example, the quarks do not appear as mass shell states, free particles, they are confined. So to define the quark mass by that pole property is not the appropriate thing because they do not appear as external particles. Okay? So there are 2 popular renormalization prescriptions called the minimal subtraction subtraction and S, or there is another one called MS bar. First of all, MS. MS is the prescription which tells you that subtract from gamma 4 just the singular piece, nothing more than that, this piece, and leave everything else as part of the renormalized finite amplitude. The condition that we imposed subtracted more than just singular pieces, subtracted this, and the whole 4 pi mu squared. But you can subtract just a singular piece, still you will get a finite amplitude. The MS bar scheme is very similar to this. It's telling you that in addition to the singular piece, subtract also gamma and the 4 pi. You cannot subtract mu squared because you have to keep this argument of logarithm dimensionless. Okay? So in the minimal, in the MS bar scheme, which is for us for this discussion is better because it simplifies the expression. In the MS bar scheme, gamma for S renormalized will be simply minus lambda squared divided by 32 pi squared. You subtract all this, everything here, and leave only the finite part, dx logarithm of mu squared over a squared. It's a squared as a function of s. Is clear? This is just prescription. Subtract the singular piece plus these constants, Euler constant, and 4 pi, etc. Therefore, the amplitude in this prescription, this gamma, the n, the total amplitude, let me remove what we don't need. So m STU in minimal in MS bar will be minus lambda squared divided by 32 pi squared I seem to have been messed up completely with these signs. No. Oh, yes, no. Here what I have is, this is upside down. God.
You have an extra minus sign, right?
Yeah.
The amplitude.
So I think this is correct. This should be correct upside down. Sorry for this. I should not do LaTeX. It is too difficult for me. Simply. Modulo the sign. You have to fix the sign. I think the sign is correct for the reason that I will tell you in a minute. So anyway, if you put the three terms together, there will be terms like this up to the sign that we will fix in a minute. So you can put the logarithms together and write it as a single term. In a compact form, a squared s, a squared t, a squared u, divided by mu to the 6. Very well-defined finite quantity, but it seems that it depends on an arbitrary parameter mu, which it shouldn't. The way it is not going to depend on mu, there is only one way, not more than one way, is that this lambda also depends on mu in such a way that the mu dependence of lambda and this explicit mu dependence cancel out up to the order that we are calculating and make this scattering amplitude mu independent. And that's going to give rise to the idea of the running coupling or an effective coupling. That means a coupling constant which is going to depend on a mass parameter, which is the same thing in theory of relativity as energy, which is the same thing as the inverse distance or distance. So that we will have a coupling constant which should be a function of distance. It will change depending on at which distance you are examining the process or at which energy you are examining the process. Okay? So the condition is that M must be mu independent. This means that dm by mu must be 0. And the only way that it can be 0 is for lambda to depend on mu. You see, remember how mu was introduced. Mu was introduced simply because mu 0, lambda 0 had a mass dimension in n dimensions. We wrote it as, there were of course also the renormalization constant. If you go back to the renormalization constant, you see that they are all dimensionless. Okay? I've defined these things in such a way that the renormalization constants remain dimensionless. And therefore the dimension for this comes essentially from the dimension of the dimension that you introduced. And the lambda 0 essentially doesn't know about mu. So that is another way of looking at the mu dependence of the lambda, or another way of understanding that. So in any case, let's go back here and just differentiate term by term. It looks like a complicated expression to differentiate with respect to mu, but you will see that, in fact, it's not that complicated. Now, instead of taking the derivative with respect to mu, normally it's common to make this a dimensionless derivative and look at the mu dm by d mu. So it's the logarithmic derivative of m with respect to mu. This has to be 0, and that 0 is the first term. There is this term here, plus the derivatives coming from the other terms. So the derivative of this term is not complicated to evaluate. It's a simple function, and it will give you minus 2 lambda divided by 32 pi squared times the derivative of lambda with respect to mu times the integral dx log of whatever is there. And then there is the explicit mu dependence here. Okay? That term gives you, there is this minus lambda squared divided by 32 pi squared outside. It is minus logarithm of mu to the 6, and that will give you minus 2 times 3, that's 6. It will just give you 6, okay? Minus 2 times 3 times nothing. Because we are differentiating with respect to mu. Actually, we are differentiating with respect to logarithm of mu. This is 6 times logarithm of mu. Since it's in the denominator, it gives you this minus. I don't know why I'm writing it in this way. So it simply gives you minus 6. Now, okay, so what's the use of this equation? This is an equation for the derivative of lambda with respect to mu. If we know that derivative, then we will know how lambda depends on mu. This is equal to 0, so we can solve this equation for the derivative of lambda with respect to mu. That has a name. So this is called the beta function, which depends on the coupling lambda, and it is defined to be mu d lambda by d mu. So this term is beta minus, simplify these things and evaluate beta. In evaluating beta, so there is a beta here and there is a beta here. So we can put beta as a common factor and take out the coefficient. Coefficient is, there's I will multiply everything by a minus sign. That minus will go away, that minus will go away, this minus will go away. So the coefficient is 1 from here plus lambda over 16 pi squared from here times this integral. Unfortunately, this will not fix us. No, it will. The same. And this minus has disappeared. This gives us 6 divided by 32, 3 divided by 16, pi squared lambda squared. Okay? This whole thing should be equal to 0. And 0 equals to this. I'm just rewriting it and substituting for the derivative beta and writing this as beta times whatever multiplies beta. So we have to solve this equation for beta.
Shouldn't there be minus sign?
Where?
The second term, because in
Yeah.
the second term, because in
Yeah.
there are 2 minus
So
signs.
we multiply that as minus sign. Thank you, yes. Thank you, yes. Actually, it's important. Now we will know what I have written was correct or not. Because if you, to solve this, you have to multiply by the inverse of this. And remember that we are calculating the terms in powers of lambda. Okay? So we have to keep those powers of lambda, which is within our approximation. This to the power minus 1 can be expanded as 1 minus lambda times this. So beta should be equal to, take that to the other side, 13 over 16 pi squared lambda squared times this bracket to the power minus 1, which is 1 minus lambda divided by 16 pi squared dx 0 log, etc. Plus other terms. Okay? Now, the first term is of the order of lambda squared. But when you come here, it's of the order of lambda cube. The remaining terms, the other terms, will have more powers of lambda. So, the beta that we are obtaining from here, that means the variation of the coupling constant, the renormalized coupling constant, when you change this parameter, mass parameter mu, has a leading term plus sub-leading term. So beta of lambda equals to 3 lambda squared divided by 16 pi squared plus the term of order lambda cube and higher. You should stop here. That's up to the order that we have calculated. Also, some miracles happen with this subject. This is called the renormalization group beta function. Run far out of my time, unfortunately, right at the critical point. I'll just say one word and stop. Okay? In order just to close this chapter. We will discuss the physics which comes from here, we will discuss later and also in the context of QED. So I do not want to spend too much time on it now. But let me just complete this. So we have an expression which is telling us how this beta, remember, is the derivative of the coupling with respect to mass. It's telling you how the coupling varies with mass. And you see that it's positive. The derivative of the coupling with respect to mass is positive. We should consider lambda as a function of mu as a curve. Okay? This derivative is in fact the tangent to that curve if you look at it in this geometrical way. And the tangent is positive. What does that mean? When this mass parameter mu of the energy changes, of course lambda changes, but its derivative is positive. That means when mu increases, lambda increases. When mu decreases, lambda decreases. When you go to high energy, this big theory becomes strongly coupled. Of course, perturbation theory will break down at some point. When you go to low energy, the coupling becomes small and the approximation becomes better and better. You can find out where the perturbation theory breaks down. To find that out, it is sufficient to substitute for beta what it was and set it equal to what you discovered, what you calculated, and integrate this differential equation. It's not difficult to integrate. It's a simple first order differential equation. Let me just write the answer for that integration. Find lambda as a function of mu. This mu0 is a reference mass. It means lambda 0 is the value of lambda at mu equals to mu0. Okay, so this relation basically relates the two couplings defined. So lambda 0 is lambda at mu0, and this relation relates lambda evaluated at the mass mu to the lambda evaluated at the mass mu0. This is the meaning of this relation. How the two couplings define that two values of the energy is related to each other. Totally finite. There is no cutoff. There is no infinity in this relation. Okay? Assume that you start from mu0, where lambda 0 is very small. Then the perturbation will be reliable in that domain. But then you go to a value of the mass or energy, which is much larger than mu0. This term will start growing. Even if lambda 0 is very small, after some time this term becomes large. And this will be comparable to 1. When it becomes large, when the denominator becomes small, then lambda becomes large if the denominator becomes small. Okay? At some point, of course, it will diverge. Where will it diverge? When this equals to 1, or when it approaches 1. And that tells you the value of mu at which the perturbation theory will not be reliable. There will be plenty of other ways of seeing the same phenomena. Just one last word and finishing for today. The same result can be calculated for QED, and we will do that. In the place of lambda, we will have the fine structure constant, and the analog of that relation that we have there will become alpha 0 divided by 1 minus 2 alpha 0 divided by 2 pi. Alpha is the fine structure constant. E squared divided by 4 pi. Times log of mu over mu0. You see that QED coupling, this is QED. It will be exactly the same kind of equation, except that this coefficient will be different, as you can see from here. This QED coupling, usually you hear that the fine structure constant is around 1 over 137. This value actually is the value of alpha. So this is the value of alpha evaluated at the electron mass. If you go to higher energies, this alpha will be large. And at some energy, when the denominator becomes very small, alpha, the perturbation theory will not be reliable. And that happens for mu equals to electron mass times exponential of 2 pi divided by 2 alpha 0. This alpha 0 is 1 over 137 if you set mu0 equals to electron mass. Calculate this energy numerically, find out how big it is. Okay? That will tell you up to which point. Of course, you don't have to reach exactly 1 in order to reach that point, but because if you go, if this approaches, if it becomes large, it's a dimensionless quantity. If it becomes large, then the perturbation theory will predict one. Anyway, this is called the Landau code. Landau was the first person to discover this and conclude that QED is inconsistent. So he also stopped people around him to do field theory. He thought that he had proven that QED is inconsistent, Well, there's a lot of discussion on that. So let me stop at this point, and sorry for going over time. If you have questions.